Now we want to, again, take a step back from impedance and make some generalizations that will actually give us even greater mileage with our impedance concepts. And we're going to do that by introducing this idea of a transfer function. Okay, so if I have a system and it's a linear system, and let's say it has an input, I'm actually going to excite it or drive it with some voltage Vs, right? And it has some output. Now that output could be some voltage here. Maybe there's a resistance inside. I'm looking at the voltage across it, or capacitor. Or maybe there's a current that's coming out. I could have one system where there's actually a current and my response is an I. Okay, maybe it's current in series with the inductor or a capacitor or a resistor, whatnot. Okay, and in the e to the st sandbox, okay, in the e to the st sandbox, i.e. linear system, and e to the st type excitation, we can write the following. We can describe I, and I'll say I of t comma s is equal to, or let's say V. Okay. Now let me cross this out. Let me do something more general. Okay. So I don't get tangled in V's and I's. We have a linear system. We apply some input X. Okay, and there'll be some output. In fact, one more try. We'll say we have some input X, we have some output Y. It's a linear system. Now in practice, X and Y would be either voltages, currents, that sort of thing. Well, exactly that sort of thing. And we could write in this case, so Y, let's see, Y of t, comma s, because it's an e to the st form, is the response to xt of s. In particular, this is the particular response to xt of s. All right? If we're going to talk about a response to some excitation, then we have to be talking about the particular response. There still would be a complete response that would involve initial conditions in the system, but now from this view, we're speaking specifically of how the system responds to some forcing. So in this, under this scenario, we can write, y t of s is equal to something. I'll call it g. Okay. Times, and it's going to be a function of s, times x t of s. Now, just as an example, let's say I had this right here. Let's say I have a inductor, and let's say I'm responding with, this is a voltage at the output. The input here, I'm going to apply some input Vs, and I have some V out here, right? R and L. I could write V out T and S is equal to, it's voltage division, impedance of the inductor divided by the impedance of the inductor plus the capacitor, resistor, times Vs of T, right? So this here would be my G of S. Notice it is not a function of time, right? It's a function just of the elements in the circuit. if we were back in the good old DC days of just having resistors, this G right here, G of S, would not be a function of S, but it would be a function of, any number of resistors in our circuit. Okay, so we can then write Y T of S, the response, divided by X T of S. What we put in is expressed as this G of S here. Let's do the same here. We do VO over VS. We would get SL over SL plus R. This turns out to be our transfer function. Okay, transfer function. Why is it a transfer function? Because it tells us how the signal transfers from the input at the left side here, where we have X being applied to the system, how it transfers over to the right side, the output, where we have a response. It tells us it's the transfer function. It's the function that describes how signals pass through our system. Now you could have many transfer functions. I could, for a given circuit, let's say that I wanted to find, at first I wanted to find V out here, or VL, right? Let's say I also wanted to know IR. Okay, so I could look at IR or IL would be like this, and if I wanted to, I could draw it this way. No need to, but I could say, okay, this is IR, right, or IL, same thing. Or more generally, I could just say I have VS that I'm applying to this, and my response is IR in this case. Up here, I was applying VS, and I was looking for VL, right, which I called VO. So what would it be here? What would IR be? Well, IR is simply going to be the total voltage VS divided by, the voltage applied divided by the total impedance, right? R plus SL. So in this case, I have a transfer function again, but it's not SL over SLR plus R, it's 1 over SL plus R. Notice that the denominators are common. That is going to prove to be extremely important. Interestingly here, look at this case, we can write this as 1 over, is it not the impedance? Looking in. Okay, and that's exactly what we have been solving before. So let's reconsider. The one-port network. Okay, where we had some Z of S, and we were applying some voltage Vs, and we had a current I. Or we were applying a current and looking at the voltage. Right, and what we'd write is, we would say I, in this case, is equal to 1 over Z of S times Vs. And here we would write V is equal to Z of S times I of S. And to find the natural response, okay, to find the natural response, IH in this first case, we would look for, so for IH, find zeros, find poles. We'll say poles of 1 over Z, right? Or i.e. zeros of Z of S. That's what we called it before, but really it's a pole here, right? And for finding V, the homogeneous response, for VH, find poles of Z of S. Okay? Now I said it this way because I want to point out something. In both cases, we're really looking for poles. We didn't talk about it like this before. Previously, when we were looking at this voltage source excitation and looking for looking at this topology where there's a voltage source, and now we're asking what is the natural response of the natural current response. We said we need to find the zeros of the impedance, which is true. We need Zs to be 0 here in order to be able to have some current that can exist while also having Vs set to 0, which is what you do for the homogeneous response. But in both cases, do you see now that if we write I is equal to some Gs, I'll call it G1S, Vs, that's for this guy, and if I write V is equal to some, call it G2S times Is, in both cases, the natural response is found by identifying the poles of the transfer function. I.e., poles of G of S are equal to the zeros of Z of S, which is how we talked about it in the past. And the poles of G2 of S are the poles of Z of S. So I'm expanding this idea of how do we arrive at the natural response of a system. Up till now, we've looked only at the simple case where we had basically some impedance, Z, and we were either applying a voltage, or we were doing one of these two. When we were finding the natural response, we either turned off a voltage source that was driving this, and we looked for IH, or we turned off the current source, and we were looking for VH. Now we're going broader, and we're saying, you know what, we can actually describe this in a more general term if we talk about the transfer function. And then we don't have to have these two rules, that it's zeros, if we're looking for the natural current response, zeros of the impedance, and it's the poles of the impedance if we're looking at the natural voltage response. We can simply say the natural response, whether it's voltage or current, will always be the poles of the transfer function. So let's go back to our example here, where we have R, 1, R, and C. And 1/4 farad. Okay, now let's say that we were going to drive this with the current IS. And I did ask for, let's say I was asking for the voltage across here. All right, and this is where we're going to really see the power of the transfer function. All right, this can be written. Okay, so find the natural response VC. Actually, let's find the complete response. Let's do the whole thing. Complete response VC is equal to VH plus VP, using the transfer function idea. Okay, I think what I'm going to do, can I change this? I want to go back and use a voltage for right now. We'll switch it up later, but let's do the voltage. Okay, so let's express VC in terms of VS. Alright, so I can do this really by inspection. It's voltage division, right? I have this, and then I have some impedance here, and I'm looking for this voltage as a function of the voltage over here. And this guy is R in parallel with ZC, which is R1 over SC over R plus 1 over SC, which is R over SRC plus 1. Right? So I can write VC is equal to 1 over SRC plus 1 divided by R1 plus R over SRC plus 1 times VS. Let me clean this up a little bit. It's a little bit messy here. We'll write this again. I'll multiply through by SRC plus 1. I have R over SRC R1 plus R1 plus R VS. And I'm going to keep cleaning it up, kind of like I did for the impedance. Function earlier. Let's see, VC. So now what am I going to do? I'm going to divide through by 1 over R1 plus R. Okay. And what does that give me? That gives me S R R1 over R1 plus R times C plus 1, because I've gathered these two together here, pulled them out. Finally, I'll write it as VC is equal to R over R plus R1 times 1 over S RPC plus 1 VS, okay, where RP is equal to R in parallel with R1, which we've seen before is 4/3 of an ohm. And then what I'm going to do now is, just to be clear, I'm going to write this voltage and this voltage as a function of S. Okay, now it is in the end a function of T, but we're going to start to drop the T and just use S. You notice that in this relationship, we do not have, like, this transfer function here does not involve T. It never will. Transfer function will never involve T. So let me rewrite this one last time, where G of S is equal to R over R plus R1, 1 over S RPC plus 1. Okay? That's a significant result for us. Let's actually plug in some numbers here. So that's going to be 4 over 4 plus 2. And this will be S. We have tau, which is equal to 4/3 times 1/4, so 1/3 plus 1. So this is equal to 2/3 times 3, S plus 3. So finally, this is 2 over S plus 3. That's our transfer function. G of S is equal to 2 over S plus 3. Now, how can we use that? All right, to find the homogeneous response, VH is found by identifying the poles of G of S. Now notice here, I don't have to worry anymore. Am I talking about a voltage response or a current response? Is it going to be poles or is it going to be zeros? It's always poles. When we write it as a transfer function, it's always the poles of the transfer function that give us the form of the natural response. And that's what's elegant about this. So there's a pole at -3. So therefore, the homogeneous response is A e to the -3 times t. Now, we need to get the particular response, V particular. Let's assume that Vs is 6 e to the -2t as we had before. So, in this case, we'll write, and here I will go back to writing Vc as a function of time, this is particular, and S is equal to G of S times Vs Ts. Alright? And we will write 2 over, now S, we're going to evaluate at S equal to what? To -2. And the reason is that our excitation is occurring at a value -2. So that actually comes over here. Right? We'll evaluate the transfer function at whatever value of S that we're going to excite the system. So now we have 2 over 3 minus 2 times 6 e to the -2t, which gives us 12 e to the -2t. And so finally we can combine the two. We can say the complete capacitor response is equal to 12 e to the -2t plus a e to the -3t. This is for time greater than or equal to 0. Actually, this can be, depends on where we define our initial condition. So it could be valid for, if we define our initial condition at -5 seconds, then it could be valid from time 5 seconds on. So we won't solve, well, let's assume, and let's say if Vc of t of 0 is equal to 0. Right? So if we started this off with the capacitor at time 0 being discharged, then we would find that A is equal to -12. And therefore, Vc would be equal to 12 times e to the -2 minus e to the -3. And this would be valid for time greater than or equal to 0. Let's go a little further. Suppose that instead of wanting the capacitor voltage, let's say I wanted to know the current through this resistor, IR. Okay? Under the same conditions where we're going to excite the system with 6 e to the -2t. So the way we approach it is express IR as a function of Vs. So now this is actually, since I already know, I know that Vc, right, Vc is equal to, all right, Vc of S is equal to G of S times Vs, right, where G of S we've already found was 2 over S plus 3. We can write IR is simply equal to 1 over R times Vc, correct? Voltage across the capacitor is the voltage across that resistance. So therefore, we can write this as 1 over R, 2 over S plus 3 Vc. S. Right, and R is equal to 4. So we have 1/2 1 over S plus 3 Vs. And we'll call this G1. Right? It's different than the previous transfer function. But notice that the poles of G1 of S are the same as those of G of S. And this you will always find. If you write, although there are multiple transfer functions for a particular system, right? Because the transfer function depends on what you're trying to relate or what you're trying to determine. Are we looking for the response current in the resistor R, or the voltage across the capacitor, or the current through the capacitor, or the voltage across R1? Any one of those would be responses to the same input Vs. And it turns out that for any of those, all of those, the transfer function will always have the same poles. So what's expedient is that if all you're being asked to find for a given system is the form, the functional form of the natural response of a system, you can write any transfer function and find the poles of that transfer function, and they'll be the same poles for all of the transfer functions. And from there, of course, you can write the e to the st terms in your natural response. The only thing that will change is, let me change this and write it this way. Okay, I'll write it like this. The difference between G of S and G1 of S is never the denominator, but at most the numerator. All right, it's the numerator that will change. So for instance, in G we had 2 over S plus 3, and in this case we have 1/2 over S plus 3. You'll eventually see transfer functions where the numerator could be S, could be a function of S as well. All right, but the denominator will always be the same, and the denominator is what gives you the S values for the natural response. So here we're very close to writing the solution. We'd say IR is therefore equal to, I'm still going to have the same homogeneous response, e to the minus 3t, okay, plus, and now what's my forced response? Well, I will have 1/2 over S plus 3, but here S is equal to, remember I excite this with 6e to the minus 2t, so I'll have this times 6e to the minus 2t, and that will give me 8e to the minus 3t plus 6 over 2, 3 minus 2, or 8e to the minus 3t, what is that, plus 3, Okay, and then if I say, what is the initial condition at time 0 here? Right? The current at time 0 is going to be whatever the capacitor voltage is at time 0 divided by R. We had defined the voltage on the capacitor we had defined as being 0. We said it was 0. Yeah, it was 0. So 0 over R. So therefore, IR of 0 is equal to 0. Therefore, A must be equal to minus 3. And so finally, I can write the complete solution, and that is 3 times e to the minus 2t minus e to the minus 3t. This is valid for time greater than or equal to 0.